To part 3 of this video series on projectile motion. In this video, we're going to be focusing on how to actually solve problems involving projectile motion. So really, by now, you should be very well acquainted with how to separate the motion into horizontal and vertical components, how to combine horizontal and vertical components into a resultant. You should also be very familiar with the key features of projectile motion, and now we should be able to identify which features we know, which features are unknown, and then be able to solve for the unknown features by using kinematic equations. Some steps for solving projectile motion questions are, first and foremost, to know the key features, which are to say that especially know that in the vertical the acceleration is always negative 9.8 meters per second squared, and to know that the velocity will be 0 when d equals max, which is to say at the maximum height, or which is to say that is the final velocity, or to say that the final velocity is equal to the opposite of the initial velocity if it comes back down to the same height. It is also important to recognize that the velocity will be constant in horizontal motion. So the key thing for projectile motion is to always separate the motion into horizontal and vertical components, or x and y components, using trigonometry. So you must always start by drawing the diagram and separating it out into horizontal and vertical components, and this in general is referring to your velocity. This will give you your initial velocity, vi, in the vertical, and your horizontal velocity, v. Once we've done this, then we can list all of our known horizontal and vertical values into a table. And remember that for horizontal we only need to find v, d, and t, whereas in the vertical we know that we always know that the acceleration is negative 9.8 meters per second squared, but we need to include both an initial velocity and a final velocity. In other words, in the horizontal you only have 3 parts, and for the vertical you'll always have 5 parts. Another thing that's interesting to note is that the time required for the horizontal motion is equal to the time for the vertical motion. We can see how this will be very useful for solving problems at a later point. One other very important thing to note down is that if the distance is down, let's say that an object is falling off of a cliff and falling down, the distance will be negative. If the velocity is down, if it's moving down, the velocity will be negative. And this is really important because we state that our acceleration is negative 9.8 because it's going down. Key to solving problems involving projectile motion is to recognize that we're going to have 5 unknowns in the vertical, and we're going to have kinematic equations which will always include 4 of these 5 unknowns. So if we're trying to find, let's say, the time, but we do not know the final velocity, we want to find the equation that has time in it, but does not have final velocity. Really, the key to solving these problems is to find the kinematic equation that does not have the thing that we don't know. So if I don't know what the time is, I want to find an equation that does not have time in it. That's the key. So now that we know all of these key steps and key procedures to solving problems with projectile motion, it's time to actually try an exam style question. So I'm going to go through a worked example with you. This is a worked example from the physics exam in 2018. It says Jimmy wants to catch a water balloon. He stands 12.5 meters from the launch position, and his hands are 1.1 meter above the top of the launcher. The water balloon is launched at an angle of 35 degrees to the horizontal, and the horizontal component of the velocity is 10 meters per second. by first showing that the velocity component of the vertical component of the velocity is 7 meters per second. Determine if the water balloon will arrive at the right position for Jimmy to catch it. Well, in this case, the question already lays out the most essential first step for any projectile motion question, which is to split into vertical and horizontal components. Well, again, if you recall, the key to doing this effectively is to draw a diagram. So let's draw a right triangle. So we've got an angle of 35 degrees. Now the key is to recognize that the velocity they've given us, 10 meters per second, is horizontal, which is to say the adjacent side of our triangle. Now, which side is the vertical side? Well, that is the opposite side from our angle. In this case, can we use sine? Well, no, we don't know the hypotenuse. Can we use cosine? Again, we don't know the hypotenuse. So what must we do? Well, we must use tangent, opposite, over adjacent. So the tangent of 35 equals our vertical component divided by 10, which is our horizontal velocity. In this case, we can find that our vertical component will be 7 meters per second. Now, which value is this in our table? Well, this will be our initial vertical velocity. But before we do that, any time that we start including our values in our table, the first thing you should always include, before you even start reading your question, you should draw this table and you should always add your acceleration, which is what? Correct. It is negative 9.8 meters per second squared. You should just know this by heart. It is essential to any projectile motion question. You need to know that the acceleration in the vertical will be negative 9.8 meters per second squared. Now we can start filling in the rest of our information. We know that our horizontal velocity is 10 and our initial vertical velocity is 7 meters per second. Is there anything else that we know? Well, we do know this distance is 12.5 meters. What is that? That is our horizontal distance. Do we know what our distance in the vertical is? Well, actually, this is a bit of a trick question. It says we want to try to find if the water balloon will arrive at the right height, at the right position for Jimmy to catch it. In this case, we do not actually know what height the ball will be at the end. Therefore, we cannot say that the distance will be 1.1 meters. In other words, we need to try to solve for this final distance. We want to find this distance and see, is it going to be exactly 1.1 meters? Well, how do we do this? We have 3 unknowns in the vertical. This means that we can't actually solve for a kinematic equation in the vertical. But what can we do? Well, we certainly can find the time it takes for the ball to travel 12.5 meters. This is simply by using our v equals d over t and rearranging. We can find that t equals the distance divided by velocity, or 0.8 seconds. So now we have what we need in the vertical to solve for our vertical distance, because we have 3 known values: time, our acceleration, and our initial velocity. We can solve for any of the other values using kinematic equations by finding the appropriate equation. Well, because we don't know the final velocity, we must use an equation that does not have the final velocity. We cannot use this equation. Obviously, we cannot use this equation. And here you can see there's a final velocity here too, so we cannot use this equation either. We must use d equals vit plus 1/2 at squared. By plugging the numbers in, vi is 7, t is 0.8, a is negative 9.8, we can calculate d is 2.46 meters. Well, by looking at this, we can see that this is not 1.1 meters. Therefore, no, the answer is no, the balloon will not land in his hands because it will not be in the right position.